So we have this RL circuit here, and after it reaches steady state, um, then the current that's going to be flowing around this circuit in this direction is just going to be the EMF over the resistance, because after a long time this inductor looks like a short. Now at time t equals 0, we're going to close this switch and simultaneously open S1. So S2 closes, S1 opens. We've got this current running through the inductor. Now, one of the properties of inductor, and any time you see anything in physics where there's a quantity that's dependent on the derivative of that quantity, this inductor is not going to let the current change instantaneously. Because in order to have that happen, there'd have to be a discontinuity in the current. If there's discontinuity in the current, then the derivative of that is infinite. And so you get an infinite voltage, right? So that's just not going to happen. What's going to happen, though, is over time, this is going to experience a decay, right? So it's going to start out at this value, but it's going to decay at the rate minus t over tau sub L. Right? It's going to experience this exponential decay, and the characteristic time constant for this is L over R. Remember, inductance is in henries, which are ohm seconds. Ohm second divided by an ohm leaves you with seconds. And so the current in this circuit is going to decay exponentially as e to the minus t over tau. And the question in this problem is determine the voltage across R at a time t equals 3.4 times 10 to the minus 4 seconds. Well, the voltage across R you just get from IR, right? And so that's just going to end up being script E and the EMF onto this exponential decay. And so this is the equation for the voltage in R as this decays. And that then at this point you just have to calculate tau sub L, you have to take in the time, you have everything you need to calculate this voltage. And that's it for this problem.